Hey, what's up, Chem Peeps? In this vid, we're going to explain the behavior of polyprotic acids in solution. Alright, so two big things you want to take away from this video. One, you want to be able to define polyprotic acid. And two, you want to explain the stepwise ionization of polyprotic acids. Alright, so as indicated in the name itself, polyprotic indicates multiple protons or multiple hydrogen ions. And polyprotic acids, therefore, have more than one ionizable hydrogen ion. Examples: H2SO4, H3PO4, sulfuric acid and phosphoric acid, respectively. These are both great examples of polyprotic acids, or acids that can ionize more than one hydrogen. So there you have it, definition of a polyprotic acid. Woo! Some things to keep in mind about polyprotic acids. They ionize in steps. In other words, you want to think about each of those hydrogen ions ionizing one at a time. And because of that, they each have a separate Ka value. However, as each hydrogen ion ionizes, the subsequent acids become weaker and weaker. And therefore, the Ka values of those subsequent acids become smaller and smaller. The example you have on your screen is of sulfuric acid. Again, notice that initially in the first step, it will ionize one of those hydrogen ions to form hydrogen sulfite, and then hydrogen sulfite will ionize again to form the sulfite ion, ionizing in steps. Generally, the difference in those Ka values is great enough so that the second ionization does not happen to a large enough extent to affect the pH. So take a look at this thriller of a chart that represents the Ka values for several polyprotic acids. Notice that the Ka values, for example, in hydrosulfuric acid, differ by huge factors. Ka1, or the first ionization, that first hydrogen ion, has a Ka of 1 times 10 to the minus 7. Ka2, or the second ionization, 1 times 10 to the minus 19. So factors different. And so even though H2S is a weak acid, HS- is an even weaker acid. So lucky for you, most pH problems just deal with the first ionization. Again, the reason being because in most cases, the difference between your initial ionization and subsequent ionizations are factors different from one another. However, there is one important polyprotic acid, sulfuric acid, that you need to be aware of. An important exception to this rule. By now you should realize that sulfuric acid is a strong acid and will completely ionize in solution. Ka2, or the second ionization, the ionization of the hydrogen sulfate ion, will contribute sufficient hydronium ion to contribute to the pH. So, important to recognize for sulfuric acid that whatever the initial concentration is of your sulfuric acid solution, that's going to equal the initial concentration of the hydrogen sulfate ion and hydronium ion when you perform the calculation for determining the hydronium ion concentration contributed from the hydrogen sulfate ionization, or Ka2. Let's take a look at how we would calculate the pH of a sulfuric acid solution that's 0.750 molar. We're told the Ka2 of hydrogen sulfate ion is 1.10 times 10 to the minus 2. Okay, so let's first take a look at H2SO4 when it's placed in water. The first ionization, or the first hydrogen that it's going to give off, will form hydrogen sulfate ion and hydronium ion. And recognize that because H2SO4 is a strong acid, we can assume that the concentrations of hydronium and hydrogen sulfate ion are going to be equal to the initial concentration of the sulfuric acid, in this case 0.750 molar. But then recognize that hydrogen sulfate ion will react with water or ionize again to form sulfate ion and additional hydronium. But hydrogen sulfate ion, or HSO4-, is a weak acid. And so to determine the hydronium ion concentration of a weak acid, we need to set up an ice table. Recognize, though, that our initial concentration of hydrogen sulfate ion and hydronium ion are going to be 0.750 molar. We do have initial concentration of hydronium ion in this case due to the ionization of that first hydrogen ion from H2SO4. Then, once you recognize that, the calculation is set up pretty much the same. You determine your equilibrium concentrations in your ice table, write your Ka expression for the ionization of HSO4- in water, plug in your equilibrium concentrations and the Ka that you are provided with, and because you're not going to do the quadratic equation on any of your AP Chem exams, we can make the X's small approximation here. That'll make the math a little easier, which will tell us that X is approximately equal to Ka, or 1.1 times 10 to the minus 2. Again, this is an approximation. So when you're trying to determine the hydronium ion concentration of a sulfuric acid solution, realize that you'll have your original hydronium ion concentration, which is equal to the initial concentration of your sulfuric acid, because sulfuric acid is a strong acid, and then you'll add to that the concentration of hydronium ion that you determined from the ice table calculation from the ionization of the weak acid HSO4-. In this case, 1.1 times 10 to the minus 2. So the overall concentration of our hydronium ion is going to be 0.761 molar. Then to determine the pH, we just plug that into our formula for the pH, which is the negative log of the hydronium ion concentration. And when we do that, we get a pH of 0.119. The big takeaway here, the second ionization of sulfuric acid will contribute sufficient amount of hydronium ion to affect your pH. All right, last thing to think about then is polyprotic acids and titrations. If we are titrating diprotic acid, for example, with a strong base, and the Ka1 and Ka2 values are sufficiently different, the pH curve is going to have two equivalence points. The first equivalence point will represent the titration of the first proton, and the second equivalence point will represent the titration of the second proton. We're going to use the example of sulfurous acid, H2SO3. When we react it with a strong base, hydroxide ion, we're going to form water, and HSO3-, the hydrogen sulfite ion. Realize that the ionization or deprotonation happens in steps. That HSO3- ion will then react with hydroxide to form additional water and the sulfite ion. And so when you perform a titration of a diprotic acid, you'll get two equivalence points. If you had a triprotic acid, you would get 3. And just notice then that the volume required to reach the first equivalence point is equal to the volume required to reach the second one, because the number of moles of H2SO3 in the first step determines the number of moles of HSO3- in the second step. Again, recognize it's a 1-to-1 ratio. So if I reacted 1 mole of H2SO3 with 1 mole of hydroxide ion, I would make 1 mole of HSO3-. And then that 1 mole of HSO3- would require 1 mole of that hydroxide ion to reach its equivalence point. So again, just take a look at this titration curve that represents the titration of a diprotic acid and realize the volume required to reach the first equivalence point is equal to the volume required to reach the second. That's it for this vid. Have a fantastic day.